Good day to you all and welcome to the second video of the HAPRA Crash Course playlist. This is Sanad. After the first video and successfully downloading all the needed software, we will now go into more depth regarding the VHDL language. If at any time the points covered during the presentation were not understood, try to either watch the clips again or search for online sources on your own. In this video, we will go over the following points of information. Firstly, a basic overview of some design components, such as the AND gate. Then we will go over some basic knowledge and information regarding the VHDL language. We will also discuss the basic structure of a VHDL model. And finally, we will analyze both the entity declaration and the architecture declaration, which are part of our VHDL model. In the HAPRA module, you will learn how to simulate integrated circuits, gates, and further down the line, more complex designs of hardware components. In order to achieve this, we need to get to know VHDL. VHDL is a hardware description language that was developed in the early 1980s and standardized as IEEE in 1987. The abbreviation VHDL stands for Very High-Speed Integrated Hardware Description Language. The VHDL language is readable from both users and machines, and that makes it equally suitable for describing designs and for simulating them with the help of a VHDL simulator. If you are a HAPRA student, we will mainly use VHDL to model, design, and simulate simple integrated circuits such as the half adder, multiplexer, and other simple gates. An AND gate is a logic gate having two or more inputs and a single output. In our case, the two inputs are A and B, and our output is the Y. An AND gate operates on logical multiplication rules. In this gate, if either of the inputs are low or zero, then the output will also be low or zero. Whilst if all inputs are high, then the output will also be high. It doesn't matter if one of both signals or input signals is high, the output will always be low if not both of them are high. An AND gate can have any number of inputs, although 2-input or 3-input AND gates are the most common. In the HAPRA module, we will use the IEC 60617-12 norm to draw our circuits, as shown in this slide right here. Please do your own research about this norm, as you will be asked in the Übungen to draw some circuits using this norm. What is shown on the slide is a basic VHDL program of the AND gate. It is completely normal if you can't understand the logic and written code on this page, so don't stress yourself about it. The purpose of the crash course is to give you the means and basic knowledge to set you up to write even more complex problems. The only advice I can give you right now is to practice. Like any other programming language, you learn VHDL, and you learn that it can only be taught hands-on. Reading a couple of sources online and watching videos on YouTube won't be enough for you to master the language. Practice makes perfect. All in all, VHDL is a powerful tool for today's computer scientists, as it is a requirement for some fields discussing deep learning, machine learning, and AI. So I really recommend you guys to take this seriously and enjoy it as you go down the line, especially if you are planning to go into such fields later in your professional life. Before we analyze the AND gate, the VHDL AND gate code, let's establish some definitions and rules of the VHDL language. VHDL knows the following relational operations. This is the equal sign, the unequal, the smaller than or equal, the greater than or equal sign or relational operation. It is really similar to Java. The only difference I can spot right away is the unequal, since in Java, the unequal sign is written using an exclamation point followed by an equal sign. Moreover, the following symbols are used for value assignments. This is used for variable assignments, a colon followed by an equal sign, and then the smaller than or equal sign is also used for signal assignments. We will learn the difference between signals and variables later on in this crash course. All in all, VHDL also has data types. All in all, VHDL also knows data types. We have a bit, which can take the values of either a 0 or a 1. We have a Boolean, which takes the value of false and true. A character, which takes all available characters. An integer, which is similar to an int in Java, takes the whole numbers. The real takes the floating point numbers, such as a double in Java. We have a string, which is a sequence of more than one character. For example, hello. Each letter from hello is a character, and the string is a sequence of more than one character. We also have a bit vector, which is basically an array of bits. So for example, 0, 0, 1, 0 is a 4-bit vector. We also have the data type time, which takes up values of time units, for example, nanoseconds, minutes, hours, FS and PS, picoseconds. We also have finally the last data type, and that is the severity level, which is used for error handling and takes up values of note, warning, error, and failure. As you write your own VHDL programs, you will be more flexible using the right data types in the right place. What you see on the screen is a basic VHDL model, which all programs follow. A design entity wraps up the whole program, the whole VHDL program, and is the basic structure of a VHDL model. Inside of our design entity, we have two important aspects, which are the entity declaration and the architecture body. The entity declaration and the architecture body are two separate entities in a VHDL model, both serving a distinct yet important goal. As we have discussed in the previous slide, the design entity wraps up the whole VHDL program and is the basic structure of a VHDL model. In the entity declaration, the I/O ports, the input-output ports of the circuits, are declared in the entity. Each port has a name, a mode, for example, in, out, or buffer, and a type, which we will later discuss more in depth while we analyze the VHDL and GOAT in the next slides. Note that the types of ports must be constrained, and not more than one-dimensional array types are accepted as ports. In the architecture body, on the other hand, internal signals may be declared, and each signal has its own name and type. Basically, the description of the design structure is within the architecture declaration. The functionality of your design is described and written within the architecture part of a VHDL model. In this slide, you can see more clearly how the VHDL model is structured. The blue part is the entity declaration, while the green part is the architecture declaration. In each and every VHDL program, the library IEEE must be called, which is a standard published by the IEEE Association and describes the definitions of logic values and also contains functions which can be called. Similar to Java, in VHDL, you can also call predefined functions and use them in your program. An example of a function is the AND keyword, which describes the behavior of an AND gate. As you can see here, AND is a function in the IEEE library, which we called on to simulate the behavior of a normal AND gate. Let's now analyze and look into the entity declaration in more depth. In each VHDL program, we have what is called reserved words. Reserved words are like the entity, is, port, and end, or all words highlighted in blue. The entity, after you have declared the entity name, which comes between the two reserved words entity and is, we have what is called a port. The entity port statement identifies the ports used by the entity to communicate with its environment. And each port name within the port is distinguished with a distinct name. In our case, input 1, input 2, and result are our port names, whereby each of these ports are further specified to have a port mode, which identifies the direction of data flow through the port. For example, the in reserved word tells us that our port name is an input, while the out keyword tells us that the AND result is an output. Note that all ports must have an identified mode. Moreover, we have a port type for each of our port names. And finally, we end the entity declaration by using the reserved word end followed by the entity name. This is the basic entity declaration format where the most important components are listed. We have the entity, followed by the entity name, followed by the reserved word is. We also have the port, and we end the entity by using the keywords and entity followed by the entity name, or you can also use and followed by entity name without using the keyword entity. Moreover, we have a generic inside of the entity declaration. Generic will be later discussed in upcoming videos. It is a more complex idea where in order to understand it, you will need to get used a bit to the VHDL language. The basic format of a port statement is also shown on this slide. The port statement is this right here. This is from the previous slide. The port statement is what is shown on this slide. And the basic format of a port statement is shown on this slide. In most cases of a basic VHDL program, such as the AND gate or simple integrated circuits, the type is declared as either an STD logic or STD logic vector. The STD logic is for 1-bit data types, and the STD logic vector is used for a bit vector data type. As for the mode, we have available port modes in VHDL. We have the port mode in, which describes that the flow is into the entity and should be handled as an input only. We have the port mode out, which describes that the flow is out of the entity and is handled as an output only. We have also in out, which describes that the flow may be either in or out. And finally, we have the buffer, which is an output that can be read from. A normal output can't be read from. We'll now discuss the architecture declaration. Basically, the architecture declaration describes the operation of the component, meaning what our program should do, what its functionality is. We also have in the architecture declaration an architecture name between the two reserved words architecture and of, followed by the entity name. The entity name in the architecture statement must be the same as the entity declaration that describes the interface to the outside world, which is in our case the AND gate from the previous slide describing the entity declaration in our program. We also have between the architecture statement and the keyword begin, we have a declaration part where signals, components, variables, and other subprograms can be instantiated. Signals can be handled both as inputs and as outputs. So it's basically a bus or a wire in order to connect two components of a VHDL model. So we have a signal followed by the signal name, and we have the port mode. Port type. So basically, this signal in our program is going to be used in the body. In the body of our architecture declaration go statements that describe organization or functional operation of the component. Basically, this is the execution part of the model. So we use our signal called AND gate to take the value using this value assignment of our two inputs, input 1 and input 2. In between them, we have the predefined function in our library IEEE, which is the functionality of a normal AND gate, and the value of this statement is then stored in the AND gate, and here the signal is used as an input and as an output. And finally, we use the same signal which we used as an output in the previous line, and we use it as an input for our output and result. And result is our out variable instantiated in the entity declaration in the previous entity declaration slides. Moreover, and finally, we have AND followed by RTL, which using these two formats of a word, we end our architecture declaration. This is the basic architecture declaration format. As we discussed, we have the architecture reserved word followed by the architecture name of reserved word. Our entity name is, and this is the declarative area where you can declare signals, variables, components, subprograms, followed by a begin reserved words. And this is the statement area. In here go statements that describe organization or functional operation of the component. This is basically the execution part of the model. And finally, we end our architecture declaration with the end reserved word followed by our body name or the architecture name. You can also use the double dash to write comments in VHDL. Comments aren't executed by the compiler, by the GHDL compiler in our case. This is it for today's video. I would like to thank you for your attention. And what I would like you to do is draw the OR gate circuit using the IEC 60617-12 norm, which I explained in this video, and then write the basic VHDL model and code of the OR gate. So you need to write the entity declaration of the OR gate. You will also need to do the architecture declaration of the OR gate and wrap it all with our design. You can follow the same steps we followed for the AND gate, which should be simple and shouldn't take more than 15 minutes of your time. I would also like you to use the signal as we have used it in our architecture declaration. We predefined a signal and used it both as inputs and as outputs. This is it. This wraps up our lecture for today. I wish you a nice day and until next time.